In this video, I'm going to talk about FastGrav's cross-section tool in a little more detail. If you haven't already watched the Getting Started video, you should watch that video before watching this one. Okay, so for this demonstration, I'm going to open up one of the example projects that comes with FastGrav. I'm going to use the sphere and cylinder example, and we'll look at that project's cross-section. So this is FastGrav's cross-section tool. You can see that it has two panels, the cross-section itself down here and the gravity profile graph over that cross-section. I'll come back to the profile graph in a minute. First, let's look at the cross-section panel. This is basically a standard geologic cross-section, a 2D slice into the Earth, the type of thing you'd see on a geological map. A cross-section is defined by 2 points, x1, y1, and x2, y2. And you can imagine taking the line connecting those points and slicing down into the Earth to produce a cross-section. Now, in a real-world gravity survey, your observation points probably don't fall exactly on this perfect line. They probably meander a bit and only loosely follow a straight path. Those observation points in FastGrav are still shown in the cross-section tool, but they are projected orthogonally onto the cross-section. So this observation point, for instance, even though it's not precisely on this perfectly straight cross-section line, is projected onto the cross-section and shown right here in the cross-section tool. So this point corresponds to this point corresponds to this point, and so on and so forth. This is an important point because it means you don't have to, and in fact you shouldn't, manipulate your geographical points before you import them into FastGrav so that they fall on a straight line. FastGrav uses a 3D XYZ coordinate system to compute gravity effects. So if you have XYZ data, like real-world UTM coordinates with associated gravity measurements, you can use those coordinate numbers directly without changing them in any way. And the cross-section tool will still allow you to visualize your data as if it were on this perfectly straight transect. All right, let's go back to FastGrav now. So in this project, I've got a pretty boring observation set. Let's open up the observation set table and take a look at it for a second. Okay, so this column of the table shows the geographic location of each point in the observation set. So you can see that we're starting at 0, 0, 0, that's x equals 0, y equals 0, z equals 0. And we're going from x equals 1 to x equals 2 to x equals 3, all the way up to x equals 100. And every single one of these observation points has 0 for the y and z coordinate. So what we've got here is an observation set that actually is perfectly straight and has no altitude changes. It just goes from x equals 0 to x equals 100. And we can see that up here in the upper right-hand corner of the cross-section tool, where the endpoints of the cross-section are defined. x1 and y1 define the first point, and x2, y2 define the second point. So those are these coordinates right here, x1, y1, x2, y2. So these are the points that FastGrav will draw a straight line between when it is constructing this cross-section. Now, by default, x1, y1 is locked to this first point in the observation set, and x2, y2 is locked to this last point in the observation set. But if I uncheck this automatic cross-section bounds box, I can change these points manually. So this is like moving the endpoints to observe a different slice of the Earth, or to look at the same slice but with a different range. So let me just change x1 to -10 And just for fun, I'll change x2 to 110. So you can see that I've essentially, I haven't really changed what cross section we're looking at, because this new range is collinear with my last range, but I have sort of zoomed out. I've moved these boundary points back. I've moved this one farther away and this one farther away, which essentially zooms out from the cross section a little bit. So I can look at this greater range if I want to do that. And all of my observation points are still projected onto the cross section, no matter what these bounding points are. This is important because it allows you to have a cross section that is actually askew to the natural direction of your observation set transect, which can be helpful for 2.5D or 3D modeling. So, bearing in mind that this observation set goes from x equals 0 to x equals 100, just in a straight line, and y is 0 for every point, I'm going to, first let me reset these x values to 0 and 100. I'm going to change this y2 coordinate to 25. So we're still looking at the same observation set, and we're still looking at a similar looking profile graph and the same mass items, but now we're looking at them from a slightly oblique angle because we've moved those boundary points so that they don't correspond with the first and last points in my observation set. And we can play with these boundary points more if we want. By playing with these boundary points, you can view your cross-section and your mass items from any angle. So let me do that. We can even look at it from a very oblique angle if we want. So I'll just play around for a second. So now I'm moving the first boundary point as well. And if you want, we can even look at it. We can look at this cross section and the mass items in the model from any angle we want. We can look at it from the super oblique angle. I hope you can sort of see FastGrav's 2.5D display there. So if you wanted to, you could view this transect from a very oblique angle, or study several observation sets that might not be necessarily going in the same azimuth as each other, and sort of switch back and forth between these different observation sets without worrying about reprojecting your points each time. Just like observation points, mass items are also displayed at their projected positions on the cross-section. Let's say you've got two spherical mass items and they're directly under your transect. This is what that cross-section might look like. However, if we move the spheres some distance away from the transect, the cross-section might look unchanged because the projected positions are the same. The main point here is that no matter where the mass item is located in 3D space, it is shown in its projected position on the cross-section. This is also true for infinite cylinder items. Let's say you've got a buried horizontal infinite cylinder running perpendicular to your transect. In the cross-section, that will be shown as a circle. A very important thing to understand about cylinders and prism items in FastGrav is that their orientation and location are defined by a center point and an azimuth. Here, this little cross represents the cylinder's center point. Please note that mathematically, a center point and an azimuth do not uniquely define a cylinder. In other words, a different center point with the same azimuth could define an identical cylinder. You can see that here. So although the center point is different, the same cylinder is defined, and FastGrav treats these cylinders the same for modeling purposes. Here's another example of how a cylinder perpendicular to the transect might look in the cross-section. When the cylinder is at a skew to the transect, that is also represented in the cross-section as a pseudo 3D looking truncated cylinder. Just remember that the actual cylinder mass item is still infinitely long in the axial direction. This short, stubby cylinder is just the graphic used to represent the infinite cylinder in the cross-section. One final important note about skewed cylinders and cross-sections. Cylinders are displayed at their projected location based on their center point. So you might have a situation like this, where the center point is some distance removed from the transect. The gravity anomaly peak for that cylinder is going to be somewhere over here. But in the cross section, the stubby cylinder graphic would still be over here. So you just need to be cognizant of where your center point is. Let me demonstrate this in FastGrav. First, let me turn off this sphere item so that we can just play with this cylinder, and I will set our cross-section bounds back to automatic. So this modeled gravity anomaly curve is only for our cylinder. Our sphere is not contributing to this. Let's take a look at this cylinder's properties. So right here are the cylinder's center point coordinates, or the axis point coordinates. So we've got an x, y, and z location. And we've got y equals 0, which means that the cylinder's axis point right now is directly under the transect. We've also got azimuth equals 0 degrees, which means the cylinder is perpendicular to our transect. You can see that graphically in the cross-section because we've got a circular graphic representing this cylinder. So let me first just increase the azimuth to 45 degrees, and we'll see what that does. This should just broaden out the gravity anomaly curve a bit. Alright, so we saw that gravity anomaly curve broaden out, and that makes sense because now the cylinder is at a skew towards our transect, so its gravity anomaly is wider. Okay, now let's move the cylinder's center point. So again, right now the center's y coordinate is at y equals 0, directly under the transect. Recall again that our transect goes from x equals 0 to x equals 100. And that's from left to right. So the positive x direction is this way. That means that the positive y direction is quote unquote into the screen, and the negative y direction is quote unquote out of the screen. So with that in mind, let's change our cylinder's y coordinate from 0 right under the transect to negative 25, or 25 meters towards us out of the screen. Since the cylinder is sort of pointed that way, we would expect to see our anomaly curve move some distance to the right. So from here over here. But notice that since we didn't change all of our cylinder's center point coordinates, the cross-section representation of the cylinder didn't change. We have to imagine it moving 25 meters towards us out of the cross-section, out of the screen. Thus, we can sort of imagine this cylinder pointing towards the cross-section and intersecting under the transect right about here, which is why our anomaly curve is here. Before we move on to the profile graph, a final reminder about the cross-section. Underneath everything, FastGrav uses observation points and mass item properties to calculate gravity effects. The cross-section is only a visualization of the underlying model. For more precise and comprehensive representation of your model, You can always check the properties of your mass items directly by editing them and checking all of these numbers. Or you can open up the observation set table, which you do by right-clicking here and choosing Open Table, which I have open already. So the cross-section is just a convenient visualization of your data. You don't have to use it at all if you don't want. You can rely completely on editing the mass items from the mass index and viewing your numbers in this table if you really want to. Okay, now let's talk about the profile graph panel. This is where your modeled gravity curve or your results are displayed. If you have empirical data for any of your observation points, that's displayed here too. In this example project, I do have some made-up empirical data, so we see two curves here. Let me make this window larger so we can see them better. The blue curve here, I hope you can see that that's blue, is the modeled gravity profile. This is what FastGrav is calculating or forward modeling from the mass item scenarios that you give it. This gray curve is my empirical gravity curve. For a real gravity survey, this would be a graph of your field data after corrections. Of course, the y-axis is in acceleration units, milligals in this case, and the x-axis is in length units and represents distance along the straight cross-section transect beginning at 0. The x-axis is always locked onto the endpoints of the cross-section. So when you change these x1, y1, x2, y2 numbers, the range of the profile graph will change as well to keep that profile graph precisely stacked over the cross-section. Let me change our mass item parameters really quickly. Set this back to 0. And we'll set our azimuth back to 0 as well. And we'll add our sphere back in. So you can see when I move these mass items, the modeled curve is being recalculated as I go. But of course the empirical curve stays put because it's empirical data, it's constant data. I entered it once and that's it. So like I was saying, the x-axis is always locked onto the endpoints of the cross-section. So if I uncheck this and change these numbers like I did before, as you would hope, as you would expect, the profile graph stays locked exactly over the cross-section. So this observation point is this observation point, and so on and so forth. These panels are never out of sync with each other. Let me reset these. Also note that the cross-section is locked into a 1-to-1 ratio with the profile graph. That is to say, these 10 meters here are visually equal to 10 meters here, horizontally, and 10 meters vertically here. If you need to see the deeper regions of your cross-section, you can click and drag on this zone of the cross-section panel. And you can see by my z-axis here that I'm just scrolling deeper into the earth. Let me drag it back up. Going back to the profile graph, I'll just touch on a couple of graphing features. You can edit the y-axis options here. Automatic means that the range of the y-axis will rescale itself to fit your profiles, whereas manual lets you specify a constant range for the y-axis. Right now it's set on manual, so let's see what automatic looks like. I will click apply. So let's increase the radius of my sphere. We'll make a really big sphere, and as we get higher up there, you can see that the y-axis is actually rescaling as this sphere's gravity profile gets greater and greater. So for a lot of projects, that's the setting you're going to use. It's a nice convenient setting. Let me scale it back down. Go back into y-axis options. I'll set it back on manual for a second. When you have manual checked, you also have specific control over your ticks. So if you really want different ticks, you can set that here as well. We'll have a tick every 0.2 milligauss instead of 1 milligauss, instead of 0.1 milligauss. So we'll see that axis become less tick busy. Anyway, that's just some graphing features. All right, one final feature, which is helpful for keeping track of the hard numbers underlying the graph, is if you hover over the profile graph, you can see the precise location of your cursor in graph coordinates. So for instance, where my cursor is right now, I am 39.2459 meters along my transect, and my cursor is at 0.326537 milligauss. And if you hover over a data point, it will light up red, and you can see the data point's real x, y, and z position. So here that's x equals 25, y equals 0, and z equals 0. And also the exact gravity value for that point. So here we've got an empirical gravity value that's indicated by EMP of 0.114664 milligauss. I find this to be pretty helpful for comparing modeled and empirical curves that are quite close together, because you can hover over those points. Let me make these curves match a little closer. So now I've got my empirical and my modeled curves matching a little closer. I can hover over 2 points, a modeled point and an empirical point, and sort of compare those gravity values directly. So here I can see that my empirical gravity value is 0.15955, and my modeled gravity value is 0.15009. So those are nice and close. I can see that graphically, but if I want to, I can also check out the numbers themselves right there. Alright, so that is FastGrav's cross-section tool. Check out the text documentation for more info, or go to fastgrav.com, or email me if you have any questions, and thanks for watching.